everyone, and welcome to the 5th talk this Michaelmas term. Welcome to Physics Society. My name is G, and I'm the president. We're joined today by members of the committee, Vivian, Rob, Alex, Ada Akash, and Yukwan. Welcome, and we're delighted to introduce you to our speaker, Professor Todd Huffman, for his talk on the search for triple Higgs bosons at the LHC.
Okay. Thank you. So yes, I'm Professor Todd Huffman, and the research that I do is at the Large Hadron Collider. So I'm going to be presenting to you part of a talk that I actually ended up giving at Cambridge. Boo. But what I did to them, you'll be happy to know that what I did to them was not only did I talk about searching for triple Higgs bosons, but I also talked about searching for double Higgs bosons. Okay, and by the time I was finished with this tour de force, they had to sit through something like 2 hours. And I won't do that to you because I'm your friend. All right? So we're only going to talk about the triple Higgs boson result, okay? Which is basically using matter and energy conversion to find out more about fundamental particles and looking for 3 Higgs bosons in the Atlas detector at the Large Hadron Collider, right? So 3 of them, not just 1, not 2, but 3 Higgs bosons. And we do this at the Large Hadron Collider, okay, which I show here in this schematic view, because unfortunately the actual accelerator is about 100 meters underground, and so you can't really see it when you fly over Geneva. So this is an aerial shot of the region around Geneva showing where the accelerator is. You can get an idea of scale because, let's see, do I actually have, yeah, this is a better idea of scale. So it's about 8.6 kilometers in diameter, okay? But you can see, oops, I want to go back, there we go. But you can see here is the runway for Geneva's airport, okay? To give you an idea how large the Large Hadron Collider actually is. There are several experiments that are at collision points. So it accelerates protons. It's in the tunnel. There are actually 2 accelerators in there, right? 2 different beams. So the protons go in opposite directions and they collide at 4 different places. There's LHC, okay? There's LHCb, and then there are 2 experiments that are really the high energy experiments, and that's CMS, which is way out here in the boondocks, and then Atlas, which is the experiment that I'm on, that fortunately is just right across the street from the main CERN site, and that's the main CERN site right there. This is an inset view of what it looks like inside the tunnel. It looks like there's actually only 1 beam pipe, but in fact, inside this big vacuum chamber, there are actually 2 beams, right, going in opposite directions. So 2 sets of magnets, okay? Now, what does the LHC actually do? All right, it accelerates protons in opposite directions, okay, in 2 separate rings within the same tunnel. We squeeze the beam's cross-sectional area. It starts off about the size of a pencil, and then we squeeze it, okay, down to about 30 microns, all right, at the experimental places. And then there are collisions. When the beams are squeezed, right, the 2 protons come together and they collide in bunches. About once every 25 nanoseconds, the bunches cross, okay? Now, the goal of this is really very simple, right? It is to get as much energy into as small a volume as possible, okay? And you can get an idea of what that volume is, all right, by using the equation that you'd use if you had the energy of a beam of light, right, at these energies, and then find out what the wavelength, how large is the wavelength of that light, okay? And so at 14 trillion electron volts, okay, we're down to a level of something like 90 times 10 to the minus 6 femtometers, okay? And a femtometer is 10 to the minus 15 meters. Another way to think of this is that a femtometer is approximately the size of a proton, all right? So we're talking about millionths, getting an energy packed into a volume millionths of the size of a proton, okay? And the protons are really just a convenient vessel for that energy, okay? It's just a mechanism by which we can take the energy from, I call it the not so coal-fired power grid, because we buy the energy from France, so it probably comes from nuclear power actually more than anything else, okay? And the protons are traveling really fast, okay? So 99.1234569999902% the speed of light, okay? And the proton is unfortunately not a fundamental particle. It's made up of lots of stuff. There's lots of things inside a proton. I've got a little schematic view here. You've got 3 valence quarks, 2 up quarks and a down quark. They have different colors because there's a color force, right? There are gluons that hold them all together. The gluons are so strong that sometimes they split for brief periods of time into other quark-antiquark pairs. The protons are really messy, okay? And this is what we're colliding, right? Are these big bags of messy things, okay? And so a natural question to ask at this stage is to say, well, you've got this really, really small distance, right, involved, this really small wavelength, 1/1,000,000th the size of a proton. Is what we are doing actually looking at the inside of the proton, finding out what's inside the proton, like you would with a microscope? And there's a clear answer to this, okay? No, that is not what we're actually doing, okay? What we're doing is really very simple, all right? We are actually making things that weren't there, okay? Because of an equation that I think every one of us in this room certainly knows. Actually, probably the whole world knows, right? I think the whole world knows that equation, of course, okay? What everyone in this room appreciates that most of the world does not appreciate, okay, is that an equal sign in physics is an exceptionally powerful thing, right? It means that whatever's on one side is identical to whatever's on the other side. And on one side, we have energy, and on the other side, we have mass, right? And so that means they are the same. We convert one into the other, and that's what we're doing. That's why we want something to get as much energy as possible into as small a volume as possible, so that we could take these objects, this is essentially the particle physics periodic table, and create them, even though they aren't necessarily there, okay? We're all familiar with a few things on this table, okay? There are the leptons, electrons. Of course, we're all familiar with electrons because we're all looking at electrons, right? Everything you see around you is an electron, okay? The way the electrons, are put together in atoms and the way that they lock together in solids means that they reflect different wavelengths of light, and so you see them with different colors, all right? They occupy all of the possible states of the solids that they're in, and so they feel solid, okay, when in fact they're actually not, right? But you're trying to put your hand through states that are already full, so it stops you, okay? So electrons are easy. Muons are a bit harder. They're passing through you at the moment, coming from outer space. About 1 per second is passing through you. But they're just heavy electrons, okay? And then, of course, there's up and down quarks, which you can't see, but they're all there because they're inside the protons and neutrons that make up all the atoms that arrange those electrons in the myriad of ways that we see around us. So we are, in some sense, familiar with those, okay? And then, of course, there's the photon, right, which is key to us being able to see everything that there is, okay? So this is the stuff that we're familiar with, but there's a lot more, right? And of course, the latest entry into this was the Higgs boson, okay, which I'm going to talk a lot more about as we go along, all right? They come in 3 different, sort of 3 different generations. This is something about the Standard Model we don't know why, okay, but it seems to be a fact. The top quark, these are the masses in electron volts. As you can see, the top quark is far, far heavier or more massive than any of the others. The top quark is about as massive as a gold atom, okay? And then you have gluons, which only interact with these quarks, okay? The W and the Z, which are responsible for radioactive decays, okay? And these represent different forces of nature, the strong interactions, the electromagnetic interactions, and the weak interactions, okay? You will notice that gravity is sadly absent from this picture. This is another thing that we've tried desperately for many, many decades to bring gravity into this picture, and have so far been unsuccessful in doing so, all right? So what do I do, right? Well, I'm looking for things generally that aren't, there's a whole sections of physics in ATLAS where at these extremely high energies, we're actually trying to measure to high precision the interactions between these things that we know exist, okay? And this is called standard model physics. But I don't do that, okay? I do exotic physics, all right? Looking for things that are in the unknown, okay? So we want to cover a wide range of final states, things that, I mean, the way I look at this is that we have this detector, all right, and this machine, okay? And if something exists that has certain properties, we should be able to see it, all right? So as far as I'm concerned, I don't care if there's a theory out there that says it should exist or not, okay? If our detector could see it, we might as well look for it, all right? And there are quite a number of people that look for various strange things. As strange things go, looking for Higgs bosons is actually quite tame, all right? But there are other models, right, that could produce multiple Higgs bosons, and we look for those too. So we try to make these things model independent when we look for new particles. New particles, we call them resonances, by the way. So sometimes if I say that, I just mean a new particle that wasn't in that list, okay? And we also look for any disagreement with the standard model, right? Does the Higgs boson that we discovered actually decay into the things we think it should decay into? Is it doing so with the right proportions? You know, these kinds of things, right? So this is the stuff that's going, or are there exotic things that Higgs decays into that we didn't expect, right? That's another aspect of exotics physics, okay? And there are people who do that, okay? And so here's a group of people who were working on this triple Higgs analysis, or are in my group. We've got James Frost, my colleague. There I am. That is the best picture I've ever taken in my life. So I'm afraid when you invite me to talk, no matter how old I am or no matter how much I no longer look that way, that's the picture you're going to see, okay? There's Holly Pacey and Bill, and then Maggie. See, I do graduate students, all right? She actually graduated. And then Thomas is, I hope, about to graduate one of these days soon, maybe. And then their new student, Ruben, okay? Bill was with us, and then he was not with us. He went to Cambridge. But now he's back in Oxford, so that's very good, okay? And I also want to bring up another person that's involved in exotics physics, because it explains why we do what we do and why we have models in the first place. What do we do with these models, all right? And that's Christopher Columbus, okay? So Christopher Columbus, yeah, so I'm gonna go back before we go forward. Christopher Columbus, what did Christopher Columbus do? Well, at the time, the big thing that would make you a lot of money is if you got spices from the Spice Islands, right? And the Italians were making a fortune because they were the gateway, right, to the East, and so they were creaming off profits, you know, from the spices that were coming up through Italy and through their trading networks, right? And so this was a big thing, you know, getting to the spice. The countries that were having to pay for this, that pay the extortionate rates, didn't like that, okay? And so consequently, you know, Spain, England, Portugal, they were desperate to get access to the Spice Islands and break this monopoly, okay? And Columbus came along and he said, you know, if I take a flat map, right, and I kind of roll it up, he says, you know, there's this, the flat map would be here and over here. And he said he realized there was an ocean, right, that to the east of the Spice Islands, there was an ocean. And to the west of Spain and Portugal, there was an ocean. And he's like, oh, that's the same ocean, right? And so he wrapped it around, right, and concluded that the ocean is small enough that a ship could just about make it from one to the other, right, and not run out of water, Okay? Now, there's a problem with this model, and everybody knew the problem with the model at the time. Okay? And that is that they all knew, since ancient Greek times, how big the Earth actually was. Okay? So they knew that if that was the same ocean, if in fact this ocean and that ocean were the same ocean, and there was nothing in between, okay, what's shown here on this map is about half the size of that ocean, okay? And there is no way a ship of the day could carry enough water, right, that you could get from this side to that side without everybody dying of thirst. All right? It was clearly going to be impossible. Okay? And everybody, at least everybody who owned ships and knew about ships, they all knew this, but that didn't stop Christopher Columbus. He had a map and he had a model, right? So he convinced, he went out and he convinced a couple of people to fund his expedition. And fortunately for him, okay, something that he didn't anticipate, right, ended up in his model. And that was, there's a whole freaking continent dropped right in the middle of that ocean. Okay? And so he ran into the continent just about the time that he was going to run out of water. All right? And it effectively saved the expedition. But needless to say, it meant that, so he had several expeditions. His first voyage, second, third, he had 4 voyages where he went to the, so-called New World. And to the day he died, he honestly thought he'd found the Spice Islands. But they weren't. They were obviously not the Spice Islands. So he figured he'd found some islands that, were further out in this ocean, and that if he could find his way through, so to speak, he'd get to the Spice Islands. That's why America is named America and not Columbia, right? Because he never really realized that he'd found a different continent. Right? It was Amerigo Vespucci who realized that it was a different continent, and so that's why it's named what it's named. Okay, so that's what we do. That's why we have these models. All right, doesn't necessarily mean they have to be correct, but they give us a framework upon which to do our explorations. Okay, and maybe they'll be correct, but maybe they won't. But if we're visual and we're paying attention, maybe we'll find something new. Okay, so what's motivating me? What's the model that motivates us to look for 3 Higgs bosons? Okay, it's the Higgs potential. Right, this is the standard model of the Higgs potential. Right, and I think you probably have all seen this on the BBC or various other places. Okay, it looks like the sort of the bottom of a wine glass. Okay, and it's a weird potential because the thing that's on the potential is the whole of the universe. Okay, so the whole of the universe starts off in a symmetric situation up here where every direction looks the same and it's right in the middle of the potential. Okay, and then at some point as the universe expands and cools, it ends up down in a state that's off-center. And it's this off-center state that allows particles to acquire mass. Okay, because it turns out the most beautiful part of quantum field theory, okay, is when everything is symmetrical right up here, okay, and it's great, it's wonderful, and it's beautiful. However, everything in the universe then has no mass, okay? And I would argue from an experimental point of view, that's a problem, all right? And so to solve that problem, we have this spontaneous symmetry breaking that puts the universe here off-center. It breaks the symmetry in the right way so that things can acquire mass, right, and still satisfy other properties that we would really like to have, like Lorentz invariance, okay? Another thing to look at it is that the potential, could change, right? We start off with essentially a potential in a hot universe right here, and then at some later time it ends up, cooling, and our universe sort of falls into a lower state, okay? So the universe starts off hot, then the universe cools, and we are here, right? Okay. And so now, what does this mean? This means that in order to get this potential to look this way, right, is very specific, okay? It actually means that the Higgs boson ends up interacting with itself, right? And so this is the kind of interaction that I'm really looking for, okay? Is where a Higgs is produced, but then splits into three. Now, obviously, this Higgs has to have a lot more energy than just a standard mass of a Higgs boson. It's got to have enough energy to be able to produce 3 Higgs bosons, but our accelerator has enough energy to do that, okay? So we are above that threshold, right? The problem is this bit here, this vertex strength, which we call kappa 4, okay? It turns out, sadly, that in the standard model, this is really, really tiny. So it's going to be really hard and unlikely that we'd actually see it. But that doesn't stop us, right? Just like Columbus wasn't stopped by the fact that the Earth was too big, right? I'm not going to be stopped by the fact that that constant is supposed to be really, really small, okay? So why 2, why 3 Higgs, okay? Well, the reason is that this standard model shape here, okay, how do we know? How do we know what that shape is, okay? Well, we don't actually, right? What we do is the theorists who come up with these ideas, they're going to come up with the simplest thing that accomplishes the job. Okay? And the job was to give mass to our particles today. And the easiest potential they could come up with that would give mass is one that looks like this. Right? But that's not necessarily the shape that it has. Okay? For example, maybe it has a shape that looks like this. Okay? I mean, we'd still, if our universe is here, all right, we'd still see the universe as it is, but maybe we're in a false vacuum. Okay? And perhaps there'll be a phase transition with the universe going into an even lower state, thus destroying the entire universe as we know it. Okay? It would be really cool. And I also want to point out how fundamentally simple this really is, this whole business of Higgs potential, all this other stuff, okay? Believe it or not, it's as simple as a product expansion, right? I mean, all of you guys know Taylor series. Well, not all of you, but many of you do, okay? And if you want to represent a cosine function, right? Well, the first thing you'd do is you'd say, well, I've got a calculator and a computer, I just use a cosine function, okay? But suppose you couldn't. Suppose you have to approximate it, right? Well, you can do it by expanding the cosine function into a series, right? A series in x, okay? And you can do that, and you know, this goes infinite. And remember the equals sign, right? Whatever's on one side is exactly equal to what's on the other side. So if I can take this out to infinity, which I can easily do with enough graduate students, then these two things are equal, okay? Now, this potential, sorry, let me go back one. This potential, okay, is nothing more than a product expansion in the Higgs field. Instead of x, okay, it's the Higgs field that we expand in, right? So we end up with a Higgs field, if we call phi the Higgs field, we end up with an expansion in the Higgs field, okay? And this is the part of the Higgs field that describes how it moves, okay, and its dynamics, basically. This is the part that gives the Higgs field its mass, okay? So this vacuum expectation value multiplied by a constant, that, it turns out, is the Higgs mass. Well, it's the Higgs mass squared, right? But then we have these extra terms, okay? And it's these extra terms that then bring us further into the shape, to bring up more and more of these wiggles, right? And in the standard model, okay, so these are the self-coupling terms, and these are the shape of the Higgs potential. Notice that there's a cube here, and there's a fourth power here, okay? And it's the, and if I go way, way back, yeah, notice that this is 4 Higgs fields, right? There's a Higgs field here, and there's 3 other Higgs fields. That's 4 Higgs fields. That effectively becomes here we go, this term, okay? That's what this term represents. It represents the production of 3 Higgs bosons, okay? With some sort of coupling constant, okay, that the standard model fixes by the shape of that potential, right? This term, right, is exactly the same sort of thing, but it's missing one of the Higgs bosons. So this is di-Higgs production, right, producing 2 Higgs bosons, again, with its own coupling constant. And depending on the coupling constants, they could be negative, okay? So depending on the strength and size of those coupling constants depends on the wiggles that you get, right? And for the standard model, it's just that shape. The wiggles are only there with enough, you know, those constants of the strength only to give you that wine glass shape. But they could be something different, okay? Okay, now why would we believe that they are something different? One of the reasons we believe that maybe there's something different is because we are here, okay? It's an application of the strong anthropic principle. We are here, right, and we are matter. As far as we can tell, all right, our whole galaxy is matter, okay? We've had visitors from outside our solar system, right? And those asteroids that came from outside our solar system are matter, okay? So every star in our galaxy seems to be made of matter. Other galaxies seem to be the same as our galaxy. They're most likely made of matter. As far as we can tell, everything we can see is matter. There isn't a lot of antimatter around, okay? It's gone. Where did it go? All of our theories, right, with one exception, and that's the weak force, are symmetric between matter and antimatter. And the weak force is really very close to being symmetric between matter and antimatter, okay? And so if you want to do this, it was Andrei Sakharov, okay? One of his things that made him famous, apart from his activism, was he came up with these conditions that you would need in order to have an asymmetry between matter and antimatter that would freeze out in the universe. One of them is baryon number violation, okay? Which I think we have just seen, right? Only just seen the first hints of baryon number violation. Another one is we need to break the charge and charge parity symmetries, right? And this is true. The weak force does this, okay? Although people claim not to the level that you need, right? But the last thing you need that always gets swept under the rug until recently is this one. You need to be out of, the universe needs to be out of thermal equilibrium, okay? And this is not as easy to happen as you think, okay? Because if you follow the standard model, all right, there's a transition. You have sort of a thermal quantum field theory here. And if you follow the standard model and the quantum terms, okay, you end up with a temperature term here, okay? And the cubic term seems to kind of disappear. But you end up with a potential that as the temperature drops, okay, you end up with a situation where the universe can adiabatically end up where it ends up, okay? And that all seems great because, you know, you add mass to everything, you give mass to things, but you do it in thermal equilibrium the whole way, okay? And so if there is this symmetry between matter and antimatter, you end up with far too little matter, right, based on the weak force for us to exist, okay? Well, how do we solve that problem, okay? Well, you solve that problem basically by playing around with some of these terms, okay? And if you play around with these terms in the right way, you can actually get a little dimple at the beginning, okay? So this is not the standard model Higgs at some point while the universe is cooling, okay? What's happening is you've got a metastable state, right? Now the universe, particularly at the very beginning of the universe, really is like a quantum particle. And as we know, and I may have to fire up my movie sequence here. Now this is, quantum particles can tunnel, right? This is a little demonstration of tunneling, okay? So here's a wall. This will disappear, I think. Maybe it won't. Anyway, This is a probability distribution of a particle, right? This is its distance, and this is where it's most likely to be, and it's headed toward the wall, okay? But it hasn't got enough energy to make it over the top, right? So if I fire this up, it works, okay? It hits the wall, right? And as you can see, the probability splits. There's a probability that we actually find the particle over here. It's somehow tunneled through the wall, right? The universe could do that, okay? And if it does, okay, then basically that's a phase transition, all right? So this term, okay, and this term, right, are basically look for the Higgs potential as it is now, because it's now been frozen out in whatever shape it has, to see if that exists, okay? So that's one of the motivations. That's the model that's motivating this analysis, all right? Now, as long as we're doing that, as long as we're looking for this standard model stuff, which is really quite cool, and I really like it, we have to be realistic. Remember I told you about this coupling constant here as being way, way too small, right? And not be expecting to ever see this thing, okay? That's also true of this one, which is the 3 Higgs one, right? We don't expect that to be very big either, okay? So what could happen that could make these things bigger and maybe make them visible, right? And that's where other models come in, okay? There might be, I mean, how do we know that the particles that we see are the only particles that are there? I mean, in fact, we also have dark matter, right? And dark matter wasn't predicted. So, you know, dark matter might couple to the Higgs boson because the Higgs boson couples to inertia. We know dark matter has inertia because it affects the rotations of galaxies. So maybe there are particles, like dark particles, like the S, that really only interact with, you know, other heavier dark particles that we might be able to make, okay? And you can enhance triple Higgs production through these resonances. You can make it more likely that they happen, right? So this is, if this exists, this is probably much more likely the kind of thing that we'd find, okay? We then look for the Higgs. Of course, it instantly decays. And the thing we look for is the Higgs decaying into B-quarks, okay? So our Higgs boson goes to a BB bar quark pair, okay? So that means in the detector, we need to figure out how to tag these B-quarks, right? And I'm going to explain how it's done and why we look for the Higgs to B-quarks, right? The reason we look for the Higgs going to B-quarks is because that's what it's most likely to go into, okay? This is the proportion of decays that go into BB bar pairs. It's enormous, okay? And so if you're looking for multiple Higgs bosons, right, one thing to do is to pick the decay where it's most likely. So that would be all the Higgs bosons, all of them decaying into B-quarks, okay? You'd think that the W's are too massive and the Z's are too massive, but actually one of them is virtual, right? So at the end of the day, you don't end up with a real W, you end up with like leptons and stuff. And the really weird thing about the Higgs, I just want to mention it, is the fact that it was actually discovered in this decay, right? 2 photons, okay? That's because the backgrounds for 2 photons are really, really, really low. Okay, so just because, you know, you've got a low branching fraction, that doesn't necessarily mean you shouldn't look for it. Okay, another cool thing is that, which I'll leave you as a question that you can ask later maybe. Notice these are photons, they have no mass. They have no inertia. The Higgs is supposed to couple to mass, it's supposed to couple to inertia. So how can it decay into 2 things that don't have any inertia? All right, we'll leave that for a moment. Okay, so the B, how do we detect the B? Well, the big way we detect the B is the fact that it has a lifetime, okay? And so when you produce a B quark, right, so these are tracks left from a B quark decay that come flying out. Now, how do I know that? Because it flew a certain distance before it decayed, okay? And that lifetime is enough that we can pick up that separate vertex. It'll fly for a few millimeters, sometimes even a centimeter, before it decays. And our detectors are sensitive enough to track back all the tracks and find out, oh, here's a bunch of tracks that didn't originate from the original collision of the protons, okay? You can add up their masses and momenta, and you can realize that, oh, that thing is consistent with a B, okay? So here's jet tagging, okay? And you look at the Lorentz invariant mass, and you look at the displaced vertex, okay? And then you can put all this stuff into, these days, we put all of it into a neural net, all right, which we call DL1, okay? And then the neural net gives us a score where something is likely or less likely to be a B jet. And that's how we identify them, okay? I'm going to skip a lot of this stuff because you guys already know it. Okay, let's see here. Yeah, there we go. Okay. All right. This is just me explaining the Lorentz invariance to Cambridge people. Well, they do a natural sciences degree, and so most of them, you guys all do real physics. So most of them, have to be reminded about the fact that, if you have something that decays into multiple things, you can work back and find out what the mass of the thing was that decayed into it, okay? And this is the performance of the neural net on B tagging, right? So here's DL1, okay? So this is the efficiency of finding the B, okay? And then this is the background rejection, all right? And so as you can see, we already have taggers that are machine learning taggers that are doing better than the one we used in this analysis. Needless to say, this is going to be, the next time we do this, we do another look, we're going to use one of these better taggers, okay? Okay, so the search, right? Reminding you why we're doing this, okay? And also, the different, whether the X or the S exists, okay? And we're trying to find that in events that look like this, okay? There's lots of jets here, okay? So you have to identify the jets as to which ones are Bs and which ones are not, all right? And you take all of this kind of information, you plow it all together, all right? And for this analysis, we did it using a neural net, okay? So this isn't the real neural net we used, but it's an idealized way it works. You take a bunch of inputs, like all the jet energies, the B tag scores, what the charge of the jet was going to be. You put all those inputs in here, the angular positions of the jets, okay? Even the masses of the jet pairs, right? Because the mass of a pair of B jets should be the mass of a Higgs boson if it came from a Higgs boson, okay? And put all that in there, then have the neural net chunk on it, and the neural net spits out a score. Does this look like a classifier that looks like 3 Higgs bosons, or does it look like background? Okay? And here are some of the inputs, and we get this Shapley plots. This tells us which of the inputs has the biggest impact and in what direction. Okay? And this is really important to do these kinds of characterizations in machine learning, because the machine learning, you don't know what it's really doing, right? So you want to make sure that it's actually using the variables you think it should be using to come to the conclusions you think it should come to. Otherwise, you could be training it on, that it knows that every even-numbered event is one that has a triple Higgs in it, okay? You could be training it on something strange, right? And then you have to worry about the backgrounds. So we use events that have only 4 Bs, events that have 5 tag Bs, and events that have 6 tag Bs. Now, the ones that have 6 tag Bs are the potential signals, okay? And these two are not. And so what we do is we look at the neural net score, okay? And we take ratios of 4B to 5B, and then 5B to 6B, but only in the low score region. We blind the high score region for 6B because we don't want to bias ourselves, right? And we apply these ratios to the high score region of 4B and 5B, where we don't expect to see triple Higgs bosons, right? And we see if this prediction here matches that one, and lo and behold, it did, thank goodness, okay? And so then the extrapolation from this ratio to that ratio can be done from here to here, and we can predict the background, right? We can predict the background underneath the potential triple Higgs signal, okay? And so this is what you end up with. Hang on a second, let me see. Yeah, this is the kind of thing you end up with. This is the neural net score, okay? This is the data, all right? And the comparison of 4B and 5B, 5B and 6B, and you can see that it was flat, okay? This is what a signal would look like if we actually saw a signal, okay? So this is 4B and 5B are background enhanced. And then we check the ratios in the full range, and it's all flat, and that's good, okay? And we do that here, all right? And then we extrapolate to the high neural net score to estimate the background, okay? And when that's all done, it turned out, then we open the box, we unblind everything, okay? And when we unblind it in 6B, the data are the dots, okay? And the blue thing is the predicted background that we would get by this method. And sadly, it all lines up, right? And this is just doing a subtraction of the data and the prediction right here, okay? And if we had something real, we'd expect it to kind of, you know, get away from that prediction at this point. So sadly, we didn't find anything, okay? So one of these is a search for the resonant particles, and the other one is this, these coupling constants, okay? These are the various invariant masses. I won't go into that. Instead, I'll go straight to the money plots. Okay? So this is, we didn't find the x and the s, right? But we can set a limit on it, okay? Because our detector is sensitive to a certain extent. And so if there were an x or an s that was above a certain cross-section, okay? So this is cross-section in femtobarns. If it were above this cross-section for this range of masses of the s and for this range of masses of the x, in this region, we would have seen it if that had been above that cross-section. So this is a cross-section limit, 95% confidence level limit, okay? So this is the first ever time that anyone had ever looked for 3 Higgs bosons, and so these are the first limits that we ever had, okay? Then we can also look for these coupling constants, okay? So this is the di-Higgs coupling constant, the kappa 3, and this is the triple Higgs coupling constant. As you can see, the standard model would be 1 on both of these plots, all right? So, you know, this would be where the standard model would be, and here it's essentially there, okay? And this is the range that's allowed, all right? Which is a little bit crazy, admittedly, but I submit that before we actually made the measurement, nobody knew any of this, okay? And so that's what we did, right? So it's worth concluding by asking what's next. The LHC is still running, okay? It's shut down over Christmas because the power bill gets too high, all right? But they'll fire it up again after Christmas is over, sometime in February or March. And so we expect at the end 5 times the current data by the end of the 2026 run. And at this point, looking for triple Higgs would be worth repeating, okay? There's already another triple Higgs analysis to 4B mesons and one of the Higgs going to 2 taus. That's in progress, right? CERN is also building an upgrade to the LHC called HL-LHC for high luminosity LHC. And this is going to run starting in 2029, 2020, or 2031 timeframe. And the brightness of the beam is going to shoot up by a factor of 10, meaning that we can collect a lot more data in the same amount of time, okay? Now, with all of this, we actually ought to measure di-Higgs production according to the standard model. I'll be really disappointed if it does match the standard model, though, okay? But we should be able to measure it and start checking the Higgs potential shape in this next run, okay? As well as improve the limits on the quartic coupling, you know, looking for triple Higgs as well. And I think I'll stop there before anybody else leaves. All right. Okay, questions? Everybody's glassed over. Oh yeah, up in the back.
So there's a lot of neural networks. So it sounds like you're using neural networks. You see when you actually have triple Higgs boson, so triple Higgs in your data. But to train a neural network, you really need some, like, a bunch of good data of that happening already, which presumably you don't have. So how would you train the?
That's a very good question. You're right. You have to train a neural net. You need examples of signal, and you need examples of background. The background is actually easy to get. The data is essentially background. Okay. In fact, that's why we had those regions, right? That we were using. Okay. Now, for the signal, we have to assume something, and so there were a couple of different signal simulations that we ran. There were simulations that were standard model simulations, right, where we produced multiple Higgs bosons. And then there were simulations where we produced X's and S's, right, of various masses, okay? And so we trained our neural nets on those things so that it would hopefully recognize, depending on which of the two analyses we were doing, whether we had an X and S or whether we had found a standard model or close to standard model triple Higgs. Does that sort of answer it? Okay. Yes?
Why is triple Higgs production particularly interesting? In the beginning, you said it's the expansion of Taylor series.
Yeah.
So you have the second, third, even fourth and fifth. Mm-hmm. So why is the third important?
Okay, well, first of all, when you get to an expansion that goes beyond the fifth or beyond the fourth, okay, those terms that I showed you are part of something called a Lagrangian, okay, which is the basis of quantum field theory, right? And it turns out that in the simplest models, right, if you get past the fourth one, the fourth power, okay, the theory becomes something called non-renormalizable, all right, which to first order, from a theoretical point of view, is a huge no-no, okay? So the first thing to do, just as the theorists, the first thing they do is they make the potential the simplest it can be, right? The first thing you do as an experimental scientist, right, is you look for things that are as close to within the bounds, even if you're looking for exotic physics, you try to stay as close to within the bounds of what we think is true as you can, right? And so that's why we haven't been looking for 4 Higgs bosons and 5 Higgs bosons, okay? You got to walk before you can run, okay? So we've been looking for di-Higgs and tri-Higgs at the moment, okay? Yeah?
So for the Higgs potential, it's supposed to be symmetric,
Yeah.
right? But if you have an H cubed term, that would make it not symmetric.
Well, it's radial. Right? There isn't really a negative. I mean, when I was showing you the potential as a line, think of that as a cutaway. Okay? It's actually, radially symmetric. And so it'd be like the radius r. If you had an r squared, r cubed, r can't go negative. Okay? Even if a constant in front of it could.
So
okay.
The phi potential with H is strictly positive.
Yeah, that's the way I think of it. Okay, I mean it's not quite like that. It's got that shape because the Higgs is a complex field, and so there's actually a couple of Higgs fields in it. But I didn't want to bother you guys with that detail. All right. Yeah.
What does the process of actually getting the data from the CERN look like? Do you have to make some kind of research proposal and then
Nope. No, there's only one experiment, the Atlas experiments. Well, there's 2 experiments, but you're on the Atlas collaboration. Okay, to be on the Atlas collaboration, you had to be either at a national lab or an institute that helped to either construct a part of that detector. All the detectors are bespoke. So your institution had to be involved in constructing part of it, or you're heavily involved in the operation of the detector or the development of the software, okay? And that's what buys you in, right? So at Oxford, what we did is the central tracking basically the whole central tracker, the thing that actually tracks those charged particles. We constructed that here at Oxford. All right, and that was then, the different cylinders. They were different cylinders of silicon detectors. Those were sent off to CERN, and then they were assembled at CERN. But Oxford has the responsibility of maintaining that system, and that's what buys us in. So as long as that thing runs, right, and it doesn't make any sense to turn that detector off just because somebody has a fit of pique, okay? You run it. If the machine runs, the detector runs. And then, because you help build the detector, you have your institution or the people on your group have access to that data as it comes in, okay? And it takes a long time to build up enough data to make a discovery. It's not like you can run it for a week and then, get a publishable result. Yes.
I didn't know a whole lot about how the Higgs field operates, but given that it's what gives mass to particles, could changes in our understanding of it inform us towards new ways of looking at quantum gravity at all? If they're linked, I don't know if they're linked at all.
I don't know. I really don't know the answer to that. It might, maybe. But I've not seen any, of all the papers I've read and the things I've seen around the Higgs boson, I've never seen them directly connecting it to gravity except through inertia, right? And the Einstein principle that inertia and gravitational charge are the same thing, okay? But that's kind of an indirect, that's not really the gravitational equations, the gravity wave equations coming out of the Higgs boson. Right? That's just the Higgs boson creating an inertia field and the inertia field then affecting space-time. Okay? And it's because of the difference in scale, right? The difference in scale in gravity is just way, way, way lower than this. Okay? I'll do my experiment that many of you have seen, right? And my gravity experiment, show you how weak it is. Look at that. I'm amazing, okay? What have I just done, right? I've beaten gravity. I can do it with 2 fingers, right? I beat gravity. The gravity of what? The Earth, gravity of the Earth. The entire freaking planet, right? Every single thing that you know, every single thing on this planet, which is 6,000 kilometers in diameter of rock, actually radius, 6,000 radius of rock, okay? And with 2 fingers, I can beat it, and 1 arm. A whole planet. I'm stronger than a planet. Okay? That's how weak gravity is, right? This is a direct experiment of the difference between the strength of the electromagnetic force, which is what I'm using to lift the glass, and the gravitational force, which is working against me, trying to lift the glass. And this is part of the reason why I think there's a real separation between the Higgs and gravity, right? It's because we really don't know, at the moment, we really don't know how to handle that extreme difference in strengths, okay? Yeah?
In the potential function for the Higgs boson, you have this phase vector phi. What does that actually mean?
Well, the phi in that case was, I used it to represent the Higgs field. Right? In quantum field theory, every single object, whether it's a particle or whether it's a fermion or whether it's a boson, right? They all have fields associated with them. Okay? The electromagnetic field is the one you're probably most familiar with. Okay, that's the field of the photon, right? So it's a particle, but it has a field that comes along with it. That one in quantum field theory is a dream, okay? Because the photon really is massless, right? And so it just works perfectly, as a quantum field, okay? The other fields, the matter fields, like the field for the electron, the field for the muon, the field for the Higgs, okay? These are all massive fields, right? And it turns out that the Higgs potential is a potential on that field. But it's weird. It affects the whole universe and where the whole universe sits. Okay? But it comes out of, trying to figure out ways that you can break this symmetry that the photon has, and break that symmetry for the W and Z bosons and actually give them mass, while keeping the whole theory still Lorentz invariant. Okay, that's a lecture for another time. I do have a lecture on that. Basically, I asked the question, how would you pretend we discover that the photon has a very small but non-zero mass, right? It turns out that there's an equation called Proca's equation that would be perfectly fine describing electromagnetism with a massive photon, and it looks perfectly fine, okay? But what you find out is that it's not Lorentz invariant, okay? Which is a big problem. And so the question would be, how do you give the photon a mass in a Lorentz invariant way, right? And in the course of doing that, which I have a lecture that you can do, you show, okay, that you have to create a boson like a Higgs boson to do that, okay? And that's where it effectively comes from. But it's more complicated with W and Z bosons because it's a more complicated symmetry, okay? But it's the same idea. Yeah, you raised your hand?
Yeah. So you said if there's a false vacuum and the Higgs field quantum tunnels or whatever it does,
Yeah.
and goes to a new minimum,
Yeah.
that would create, I'm guessing that would release a lot of energy and
Yeah.
cause issues.
Yeah.
Yeah. So
What would happen is if it would happen in a certain region in space, okay, and it would begin to propagate outward because that's a lower energy state, okay? So the moment it would appear somewhere, right, it would be favored, okay? And so that boundary would propagate outward at essentially the speed of light, okay? And so it could be happening right now, and we just don't have any idea. It just hasn't reached us yet, okay? But that boundary, okay, that phase transition boundary, the universe is definitely out of thermal equilibrium. Okay, and it's on that boundary that you might get a situation where you have an asymmetry between particles and antiparticles. That on one side it's perfectly symmetric, and then the boundary passes through, and with the action of the boundary and the forces, on the other side you end up with more of one than the other. Okay, and so that's why I think the Higgs potential is not that simple object that the BBC always shows you. Because we do have more matter than antimatter, and it requires the universe being out of thermal equilibrium. And the closest theory we've ever had that could produce such a situation in the early universe is something like different coupling constants for the 3 Higgs and the 4 Higgs interactions. Okay, and so that's really why I really want to look at it, because I think that that's enough evidence as far as I'm concerned to indicate that it's worth trying to find. Yeah.
The same thing happened when it went from being at the center at the maximum, or local maximum, to going down to a minimum.
Yeah, well, that's when it tunneled through at whatever location the universe started doing this, right? That's what created the phase transition. Yeah. Okay, or at least in some theories, that creates the phase transition. That creates this phase boundary. On one side, it's still sitting, at the center, and everything's massless. On the other side of the phase transition, things have been given mass, and the universe is sitting at a lower energy state. Okay? And that boundary then propagates out.
So that energy that was released was basically the mass of the...
Well, it's the energy within free space itself. Okay? It's kind of like a different zero-point energy. For those of you who've taken second-year quantum physics, it's like the infinite square well. It's like having 2 infinite square wells where there's a difference in zero-point energy, okay? And you can be on one side or you can be on the other side. You can imagine a barrier between them, right? And your particle could be confined to one side and then tunnel through to the other one, okay? Yeah, it's weird. It really is. Quantum physics is very, very weird, right? Which is why I like it so much, right? Okay, maybe we should end things. They've sat here for a long time.
Thank you very much, Professor Huffman, for your teaching and inspiring us. Thank you everyone for attending. please feel free to come down to ask Professor Huffman any further questions you have, and there's pizzas waiting in the lobby. Thank you.